Okay, hello everybody. I'm Jorge Ruiz de Eguílaz. I work for Ruckus Networks, and I'm going to talk about how can we improve the user experience in real-time applications like video and voice. Right? So the key parameter here is latency. So let's measure it. How can we do it? Okay, we have here a server and connected to an access point, also to a NAC, and the NAC is in turn connected to the access point via Wi-Fi. So we have a traffic generator in the server generating 3 flows, 4 megabits per second each one. They are sent out to the access point, then to the NUC, then back to the server. Each packet, we measure the time when the packet leaves and when it gets back to the server. And this measurement is done with the same clock. So the latency measurement is really accurate. Good. In this scenario, latency is going to be fine. There's no congestion in the access point, so latency will be low for the 3 flows. But in a real context, when the network is congested, we can simulate that with this bulk traffic down. Okay. Then this bulk traffic will have an impact on the 3 flows. The latency will be much higher, and the impact will be the same on the 3 flows because all of them are placed in the same default queue, the best effort queue, right? And we don't want that. What we want is to keep latency of some specific flows as lower as possible. So what can we do? Okay, let's mark the traffic. So we mark one flow with voice, another with video, and the other one we keep it with best effort. Now let's see what happened with latency. Hopefully, latency of voice and video will be lower. Okay, let's see this experiment, the results of the experiment. To understand this graphic, we need first to see how it is built. So for each value of latency in x-axis here, latency in milliseconds, logarithmic scale, okay, according to human perception of latency. For each value of latency, for example, 20 milliseconds, we measure the number of packets that have exceeded that latency, that have been late, okay? In this case, for 20 milliseconds, if we look at the voice curve, it's 1% of packets, okay? 1% of packets have been late, more than 20 milliseconds. Right, this is to understand the graph, but the interesting question is the opposite. It's okay, let me know which percentage of packets you can afford to lose to keep the user experience, and then I'll let you know what the latency is your flow. Good. If we look at, for example, the 5% in this example, okay, we can afford to lose 5% of packets, then the latency of voice have been 15 milliseconds. For video, 20 milliseconds. For best effort, 66 milliseconds. So we can see here, we have demonstrated with this experiment that queuing makes a big difference, right? So the latency of voice and video is much lower than best effort. Okay, then where is the issue? Well, let's look at this case study. It's a FaceTime flow. This endpoint connected to this access point, the network, another access point, and another endpoint. We can see here the packets of this radio on the left. And we see the upstream. Here, this is large packets. This is video. And video is marked with TID 5. Audio packets, small packets, are marked with TID 6, okay? 5 for video, 6 for audio. So it's good, but DSCP, we can see that is 0. Okay, client devices, client applications don't mark DSCP. It keeps at 0. So what happened here in the access point? The access point removed the wireless header and placed the packet into the wire without the TID, because the TID is a field that is within the wireless header. So TID is lost. Then when the packet reaches the other end, what happened? That this access point doesn't know that it's a priority packet. So it just places it in the best effort queue. Okay, in the other way, it happens the same. So packets coming from here, okay, the returning flow reach this access point, and it places the downstream in the best effort queue. Okay, we can see this here, no TID, okay, so downstream is not prioritized. So what's the result? You can imagine if we generate here bulk traffic, congestion, what will happen? Okay, for sure, you know. Let's see this experiment. We have a laptop on the left, tablet on the medium, with a FaceTime between them, okay? The mobile phone is not participating, just taking the video, and this one is not participating, just used to create the bulk traffic. So at the beginning, we can see this is the device we are looking at, okay? The FaceTime call is fine, okay? Works fine because there's no bulk traffic. Now let's inject the bulk traffic and see what happened. Okay, it's frozen. The FaceTime call is not working properly. There is a lot of delay. Now it's frozen the image. It may change, right? But latency is really high, so we can say that bulk traffic has killed the FaceTime call, right? Well, if we stop the bulk traffic, then hopefully the FaceTime call recovers, okay? Not yet. Let's see what happens if we stop it. Okay, now we stop. Look here. Okay, we got it. Again, it's working again. So with this experiment, we have demonstrated that bulk traffic is killing the FaceTime call. And this is because we are not prioritizing the downstream. Well, what could we do? If client application is not able to mark the DSCP, why don't we do in the access point? Well, we could do it. Fine, let's do it. Then we have this on the radio, right? These packets, and now we remove the wireless header, no TID anymore, and now on the wire we have the DSCP value, the right DSCP value, so hopefully these packets reach the other end, and this access point can recognize this priority and place in the priority queue. But reality is different, okay? As you could imagine, it's very likely that DHCP value is lost anywhere in the way, okay? There is a lot of networking devices, switches, a router, firewall, the internet. So at some point, it's very likely that the DHCP is overwritten with 0. What does it mean? That, again, we have the same problem. The packets reach here, DHCP is 0, so it's placed in best effort queue. We have still the same problem. It's not solved. Well, some time ago, a client vendor asked us, hey, what if your APs communicate the wireless capacity to my client device? Okay, we could do that, but why do you want that? And they say, yeah, no, it would be useful because if we know the wireless capacity, we could start a traffic shaping process. Well, a reverse traffic shaping process, because the client is able to identify the real-time flow, okay, and differentiate with the low priority flow. Then the client could drop packets in the low priority, and hopefully the other end in transmission could lower the transmission rate, right? This could work if it's a TCP flow, okay? TCP has a mechanism to control the transmission rate according to the capacity in reception. But, well, if you do that, okay, this is consuming less bandwidth, so the impact of on the latency of the real-time flow is less, okay? So this could eventually work. The thing is, Okay, you can draw packets of the flows that are going to you, but you cannot draw packets going to other clients connected to the same access point. So this is not going to work. Okay, and also, other point, even if you are the only one that is connected to the access point, are you telling me that I have successfully delivered a packet to you that has crossed the whole network and has used an invaluable airtime, and you are dropping it? This is not good. Okay, there is something wrong. We are doing something wrong. There should be another way to solve the problem. Okay, so let's have a look again to this capture, and it's very easy to identify that these packets are the downstream. Okay, the IP addresses are the same but flipped. Ports are also the same but flipped. In this case, it's the same port, but anyway, it's very easy to identify the protocol is the same, okay, UDP. So it's easy to identify the downstream flow that is the returning flow associated to the upstream, the same call, okay? So what if the access point process these packets with the same priority as the upstream? Yes, let's do that. That is, the upstream is marked with video as 5. Let's put this packet in video queue, okay, with TID 5, right? If we do that, now we have the bulk traffic in BC4 queue, and the downstream flow is in the high priority queue. Let's look at the result. As you can imagine, okay, we can start, okay, no bulk traffic at this moment. It's fine, working fine, same as before, okay? Now, let's see what happens when we inject the bulk traffic, okay? We start the bulk traffic, and look here, okay, we got it. Now, it's working fine. It looks like no glitches, okay, responsive, very good. So with this, we have demonstrated that if we do if we do queue in and place the downstream in the priority queue, then it's going to work, okay? Let's look at another example. Here, we have done a before and after comparison. Now we are going to compare two devices at the same time, and we can see what happened. This is our office, okay? This is an access point. These are the employees here, okay? This is the internet, team server here, and this is our remote client. We have here the very well-known Jim Palmer. He's going, yeah, all of you know him. He's going to do a webinar, and he has a lot of very interesting things to tell to us. So we don't want to miss it, right? So here we have the also very well-known Peter Curry and the not-so-known Jorge, that is me. We want to attend this webinar. We want to listen to Jim Palmer. So what we do, I go to the office, and I connect to the corporate network, the normal network, that has no QoS mirroring. QoS mirroring is disabled here. And Peter is smarter than me. And he says, OK, I'm going to configure another SSID with QoS mirroring enabled. And he connects to this other SSID, right? So now, what's happening here? The video from Jim Palmer is going down from the internet, reaches this access point, and is sent out to my laptop on the left and to Peter's laptop on the right? And it's the same access point. So packets are flowing on the same access point on different queues. We are going to see that. And here, this is a server creating congestion with bulk traffic. So now let's have a look to the video on the left, that is me, and the video on the right, that is Peter. Okay? We can see the difference. And here looks good, and here looks not so good. Okay? Here we have channel utilization 95%, okay? And we can see this is fine, and here we see pixels, we see some delay, some glitches, okay? So this is because teams adapt video resolution, video quality to network conditions. If we look at the packets, okay, the packets of the flow on the right are on video queue. They are marked with TID 5, so are placed in video queue. If we look at the packets on the flow on the left, TID is 0, so they are placed in best effort queue, right? So this is the difference, okay? High quality video on the right and low quality on the left. So we have demonstrated again that QoS mirroring makes a big difference, right? Okay, how can we implement it? The Wi-Fi Alliance proposed in 2021 the QoS Management Release 1 program. And it's based in a very simple protocol. It is MSCS. It's just a request and a response, okay? The request is just the client saying, hey, access point, please, I want you to mirror the QoS of these user priorities. In this example, is 4, 5, 6, and 7. Okay? So please, mirror the QoS of those ones. And the access point just says OK or no. Here, successful is OK, I'll do. Well, this is a good implementation. The thing is that clients need to support MSCS. So there is a lot of clients that are not supporting it. Now, we have some clients available, but some others will never. Who knows? So the question is, why do we need to wait for clients to support MSCS? Why don't we just mirror the QoS of all priority flows automatically for all clients? If we do this, this is another implementation that is called unilateral QoS mirroring. And if we do this, then all clients will be supported. Legacy clients, MSCS clients, non-MSCS, all of them will be able to benefit from QoS mirroring. So you can see this is a very simple way to improve a lot the user experience on real-time applications. Thank you to Peter Curie, to Jim Palmer, and please stay here this evening. We will be here in this same room for the Ruckus vendor session later today. Thank you very much for your attention.